Professor Hudson, and I'm here to walk you through the introduction of Hess's Law. So we're going to look at thermochemistry and how we can use that to measure the enthalpy of a reaction. So let's take a look at reaction enthalpy. So enthalpy is what we call a state function. So it only depends on the initial and the final states. So what you can kind of think about that is there's more than one ways to measure the enthalpy of a reaction. So let's say we had some sort of final state, and over here we had some sort of initial state, which we'll call F and I. So what enthalpy means is we can measure it, say, directly, and in the second reaction you're going to see performed today, that's exactly what happens. You can go straight from initial to final and essentially measure it directly. Okay, but we also have different methods to measure the enthalpy that aren't as direct. So you're going to see that in lab today when we measure reactions 1 and 3 and we combine them together to give us reaction 2. So it's like we're measuring the reaction in steps. And if we take those steps and we add them together, we get the overall reaction. So for the second part of the lab, where we're kind of measuring it in steps, it's more like going initial and then over here and then back around and down to the final. We still get there. It just took us a little bit longer, a little bit sort of different route to get there. Okay, so let's take a look at what we're measuring today. So reaction 2 is the direct reaction, and that's the reaction of dissolving solid sodium hydroxide into hydrochloric acid to give us sodium chloride and water. So we're going to measure the heat associated with this process for some given quantities of sodium hydroxide and water and calculate the enthalpy. And then in sort of another part of the lab, we are measuring reaction 1 and reaction 3. So reaction 1 is sodium hydroxide solid being dissolved into water. So we're going to measure the enthalpy associated with that. And then finally, reaction 3 is aqueous sodium hydroxide plus aqueous hydrochloric acid to give us NaCl and H2O. So if we take reactions 1 and 3 and we add them together, we get 1, 2, 3 products that come from NaOH solid, NaOH aqueous, HCl aqueous, and we get 1, 2, 3 products that we get from NaOH aqueous, NaCl aqueous, and H2O liquid. Okay, so what happens then is once we sum them together, anything that is the same on either side, we call those intermediates, we can eliminate. So aqueous NaOH cancels with aqueous NaOH on each side, and we're left with the sum of these two reactions being our direct measurement of reaction number 2. So according to Hess's law then, if we take the enthalpies of reactions 1 and 3 and add them together, it's going to be the same as reaction number 2. So hopefully you'll see that in lab. It should be pretty close. Okay, so calculating the enthalpy from heat. So at constant pressure, the heat transferred in a process is called the enthalpy. So we're looking at reaction enthalpy, so delta H of reaction. So reaction enthalpy is the heat associated with a particular reaction, but it is scaled to the stoichiometry of that reaction. So when we're calculating or reporting the enthalpy of a reaction, we do have to change it into, again, to match the coefficients of our reaction. So for example, let's take a look at a reaction where we have carbon disulfide reacting with oxygen to give us carbon dioxide and sulfur dioxide. So for this particular reaction, the enthalpy is negative 1075 kilojoules. So we have an exothermic reaction that produces 1075 kilojoules for every one, this is a 1 here, 1 mole of carbon disulfide. Okay, so that's the enthalpy of that reaction. So if we wanted to look at different quantities, then it kind of becomes the heat. So let's say, for example, we had only a half a mole of carbon disulfide. So that enthalpy, that negative 1075, would be in half, and we'd only get 537.5 kilojoules of energy being released if we only had half of the amount. So that would be Q for that process, for that half of a mole of carbon disulfide that would be reacting in that particular process. Okay, so now let's look at Hess's Law. So we're going to use that same reaction, but now we're going to look at, instead of, say, measuring it directly, which we kind of just saw on the last slide, maybe looking now at measuring it in individual steps. Okay, so let's look at our reaction. On the reactant side, we have our carbon disulfide and our 3 moles of oxygen gas. So that's right here. So the direct method is D, where we then get our CO2 and SO2, our products there. Okay, but let's think about this in terms of steps. Okay, so we could take that carbon disulfide, and let's say we took that and broke it apart into elements. And that's going to correspond to reaction A. So carbon disulfide plus carbon to yield carbon solid plus 2 sulfurs. Okay, so that is reaction 3 right here. So in order to utilize this, I had to reverse that. So notice that my 87.9 kilojoules turned into negative 87.9. Okay, so again, I wanted my carbon disulfide to match up with the carbon disulfide in my original reaction, so I did have to reverse that. So again, that's the energy that would be associated with breaking essentially up the carbon and the sulfur into elements. Okay, so then B and C, now that we kind of have broken things up, we have carbon element and sulfur, and we have our oxygen that we started with, we can now start combining things together to make products. So let's take a look. So step B could be, for example, the carbon produced in step A, combining with 1 of our moles of oxygen gas that was an original reactant to yield carbon dioxide. Okay, and the energy or the enthalpy associated with that is negative 393.5. Okay, and that is given as reaction 1 up here. Okay, so using reaction 1, we produced our CO2 gas, which matches the CO2 gas from our overall sort of desired reaction. Okay, then our last step is combining the sulfur, the 2 sulfurs we produced in part A, with the remaining 2 moles of oxygen left over. So that would be our step C. So 2 sulfurs reacting with 2 oxygens to give us 2 sulfur dioxides. So because for this one here, we have 2 sulfur dioxides that we need to make. So the enthalpy of this one is double of this. So since we have double the quantities, 2 sulfur, 2 oxygen, 2 SO2, we had to double that reaction too and double the enthalpy. Okay, so according to Hess's law, we're sort of measuring this one in steps A, B, and C. If we add the enthalpy together of A plus B plus C, that should equal the overall enthalpy of the reaction. Okay, so measuring it in steps A, B, and C, add those together, it gives us the same enthalpy as if we were to measure it in just one step. Okay, so finding the heat of a reaction. So how do we go from the heat of the reaction to being able to report the enthalpy of the reaction? Okay, so we're going to run through an example of this because I think this one's best seen by doing an example. So we're going to calculate the heat and the enthalpy of dissolving 5.75 grams of calcium chloride into 245 grams of water. When this is done, the temperature of the solution increases from 19 to 23, and assume the specific heat of the solution is that of water at 4.184 joules per gram degrees Celsius. Okay, so let's look at how we're going to solve this problem. Okay, so first, a nice reaction is in order. So we have that up here. So we have a dissociation reaction, calcium chloride dissociating into calcium ions and 2 chloride ions. So we're ultimately after what the delta H of this reaction is, similar to what you're doing in lab today. So we're solving for delta H of the reaction. Okay, so really the only formula we have to calculate Q is Q equals mc delta T. So we're going to utilize that. So Q equals M is mass. So this is the mass of our solution. Okay, so it's going to be the mass of the water plus the mass of the calcium chloride that we dissolve into it. So we add the 245 plus the 5.75, we get 250.8 grams. Okay, so they told us to use the specific heat of water. So we have 4.184 joules per gram degree Celsius, and that's multiplied by our difference in temperature. So our final, which was 23.0, subtract our initial, which was the 19.0, and those are units of degrees Celsius. Okay, we multiply that through, and we get the Q of the solution was 4,196.5 joules. So that solution increased in temperature by taking in or absorbing 4,196.5 joules of energy. So the question is, of course, like, where did that energy come from? So energy is conserved, it spontaneously doesn't just start producing energy for no random reason. So it had to come from somewhere. We kind of look at what happened. That energy came from the solid actually breaking apart into ions. So when that solid broke apart into ions, it caused the temperature of the solution, which is mostly water, to increase in temperature. So in relation to the reaction itself, that's the opposite sign. Energy was released from that process, so we have a negative delta, negative Q. For the solution, it absorbed that energy, so we have a positive Q for that. So for the reaction itself, we're going to end up with a negative. This is an exothermic process. Okay, so that's Q. Now our job is to find the delta H. So we do have to scale that to the stoichiometry of the reaction, aka we need to find out how much energy is released when 1 mole of calcium chloride dissolves in solution. So to do that, this is a nice little formula here. Our delta H of the reaction is going to be our Q of the reaction divided by moles. Okay, so I'm going to take the Q of the reaction in kilojoules, and I'm going to divide that by moles. So now I'm just going to look at the calcium chloride, that is the 5.75 grams. I'm going to divide that by the molar mass of calcium chloride to get the moles. So I had 0.05181 moles of calcium chloride. So then for my enthalpy of the reaction, this is my Q, okay, turned into kilojoules, and this is my moles N. So we have negative 4.1965 kilojoules per 0.05181 moles to give us the enthalpy of the reaction at negative 81 kilojoules per mole of calcium chloride. Okay, so this is our enthalpy, where again, we took that heat and divided it by moles to be able to report it as the enthalpy of the reaction scaled to the coefficients of the reaction. Okay, so these are the calculations you're doing in lab today. You're going to measure a temperature difference. You're going to look at a salt, sodium hydroxide, dissolved into water or reacting with an acid. You're going to do the same thing that we did here. You're going to calculate Q. Then you're going to, from Q, calculate your delta H. And from that, you will get your enthalpy of the reaction. And again, because of Hess's law, what you get for reaction 2 should be equal to the sum of the enthalpies we get from reactions 1 and 3 combined. Okay, so I'm going to leave you now to go and watch the lab portion, and good luck.
Okay, so now we're ready to weigh out our sodium hydroxide pellets to be used in the first reaction. A few comments about this chemical before we get started. First things first, sodium hydroxide is hygroscopic, meaning that it can't absorb water from the air. So you don't want to take your sweet time after you weigh it out. You want to be quick. So as soon as you weigh it out, you want to get it right into the water. Additionally, hydroxide is pretty caustic. It is the active ingredient in numerous household chemicals, things such as Drano, Comet, oven cleaner, things like that. So be careful. Additionally, I want to mention here that if you get a pellet in your hand and rub your fingers on it, it feels soapy. And the interesting thing about that, it's actually not the hydroxide making the soap filling, it's your own flesh making that filling, because you're converting your own fat molecules into soap by saponification with hydroxide. A reaction we cover in full detail in organic chemistry too. So that in mind, I want to go ahead and get my 2 grams weighed out for our experiment. So I did want to mention here that these come in as pellets. And because they're hygroscopic, you don't want to leave these on the bench if they drop on the bench, because they will stick to the bench and solidify and be extremely difficult to remove. So if you drop a pellet, please pick it up. So,
That's pretty good.
looks pretty good. Just about 2 grams. First try. Awesome. All right, let's go back to the experiment now. So now that we have our pellets weighed out, I also have measured out 100 milliliters of water that we're going to dissolve our pellets into. But first things first, take a look at a little bit of our setup for our instrumentation here. So here we have a coffee cup that we're using as our calorimeter, temperature probe that is communicating to our computer here via the Vernier Lab Pro. This just allows them to talk to each other. And this is our Logger Pro software, which is going to log the software or log the progress here. So, need a new coffee cup. I'm going to go ahead and place the water in here. Looks like our starting is 20.8. All right, so I'm going to go ahead and hit start here. This will log the data for about 2 minutes. Sorry, 200 seconds. I'm going to start it and then add.
Wait. We'd like to ask you to overwrite. Yeah.
Yep.
So erase and continue.
Erase and continue. All right, so now that we're started, I'm going to go ahead and add my pellets in. And then I'm going to keep stirring with this to make sure that everything is getting mixed up together and not sticking to the side of the walls here. All right. Okay, in order to get the actual data from here, we're going to go do analyze and statistics. Is it?
Yes.
And then we'll look for the min and max here. Okay, so it says the minimum here was 20.77 and our maximum was 25.59. Okay, I went ahead and weighed out the next sample here, so we have more pellets for the second part of the experiment, and there is your weight. Make sure you write that down, you're going to need it for the calculations later. Okay, we're all set up now to do the second part of the reaction lab today. So here I have 150 mils of the 0.5 molar, sorry, 125 mils of the 0.5 molar HCl. So we're going to go ahead and get it in the cup. And then I like to make sure the temperature is kind of set before I hit go on this. Okay, I think we're going to go ahead and start it, and then I'll add the pellets. Okay, so once again, this is reaction 2. Solid sodium hydroxide with the aqueous HCl. All right. So this run is done. So just like last time, we were going to analyze the data to get the min and max, which you're going to use for your delta T in your calculations. So analyze, stats. Okay, so I am seeing the minimum here to be 20.74, and the maximum was 30.33. We're ready to do the last part now. So we have our two different acid and base solutions. So here we have our acid, HCl, 0.5 molar.
No, 1 molar.
Sorry, 1 molar HCl.
50 mils.
50 mils, and
1 molar.
1 molar NaOH, 50 mils as well. So I'm going to go ahead and add the acid first and get initial temperature, and then I will add the hydroxide. So acid first. And then I'll start the measurement on here to get our initial readings. And then I'm going to go ahead and add nice jump in temperature there. All right. Now we keep stirring and wait for the time to elapse. All right, good. Okay, so we're now go ahead and the run's done. We get our data, so I'm going to analyze again. So analyze stats, and looks like our minimum was 19.95, and then our maximum was 27.91. Okay, so now that we have all the change in the temperature, the rest is all calculations. Enjoy.